Hi friends, today I am going to discuss one of the important project like a ARMA model. I have already discussed like a AR model and MA model. So now we will discover like a ARMA model, means it is a combination of the AR model and the MA model. So we can see, yeah, we have seen here in this already in the two previous video. I think so. Most of the theoretical part, and also I have done like a practical part. If you don't have the idea about like a AR and MA model, so both has individual videos, so you could see here. So see here, and so today I am using the some other platform. So because my Google Colab ID is not opening, I think I have gotten the some emails problem, so don't worry. So let's see, just today I'm using a notebook, and this is a Kaggle notebook. So let's see, just first in this a model like a ARMA model, it is a simple model, and development like this model, the development over the time of the one variable can follow the multiple process at the same time. So ARMA model separately, just we have already discussed like a AR model tries to predict the future by a multiplying a past value by the coefficient, and this are AR process based on the presence of autocorrelations, and the target variable present value is correlated to the past value. But MA model does not use the past values of the target variable to predict its future, but rather uses the error of past predictions as an impulses for a forecasted value. So ARMA model is nothing more than the model that allows the both of these process like be in a place at the same time. So part of the futures of a variable is explained by the past values like a AR effect, and part of it's explained by the past error like a MA effect. So mathematically we can already define this model like a, if you write ARMA model, so xt will equal to c constant plus error t plus sigma I will equal to 1 to p and phi I x t minus I, where phi is the multiples of the past observations, xt minus I for the number of lakhs defined as a, and plus like another sigma I will equal to 1 and will still q, and theta t, and like theta t means theta t is a multiple of the past error like a e t minus I epsilons for the number of lakhs q, the MA order. So AR and MA model. So for P and Q are the same hyperparameter. Just I told you, just I will start from the 1 to P in the AR model, and I will start 1 to Q as a MA model. So ARMA model P and Q remains the same, and this give you like a ARMA PQ. So we could say like a ARMA PQ. This is the notations. So just there is no dependency between like a P and Q. There is no dependency between the AR and MA. definitions in the equation. So this means AR, if I speak like a ARMA P Q model, it can take the order of for P and Q. So in the special case, P will equal to 0, which means you have an MA model, because P is 0, which means, and which if you have an MA model like a Q will equal to 0, means AR model. So P and Q are hyperparameter and they are the parameters. So and another we have taken like a C and phi and theta, these are the coefficient of the model. So let's first, I am going to the collect data. I am collecting a data like a sun sports data. So it is available on the like a Kaggle's platform. So there is no need to go anywhere. So you can collect this data. First I import the pandas as a PD, and this one is the sun sports data and is the well known, having if a specific pattern of the seasonal effects over like a 11 year. So let's see, just I have click here and it has been imported this data. Okay, so preparing here the downloaded this, and after this data head, so we can see in the data head also. So it takes time, don't worry. Yeah, it has been imported, and now I could see like a data head. So I have seen here the data like a 0, 1, 2, 3, and date has been given like this pattern is a monthly mean total sports number has given like this. After that I want to get here the some information about the data, just we have already discussed. So we could see here there are 3265 rows, and 0 is the date, month, and 1 is the mean total. Okay, after that I am going to the write here some algorithm like the extract of the sunspots like a data and year. So I am going to the convert, because your data as the month way, you could say this is the monthly data. Means you could see here, but I want to the convert here, so as yearly, so need to here like data square brackets year, and need to get here the something more like this. Okay, so yearly like a year, and data dot date apply lambda x colon x and -4 colon 4 here, and data dot the monthly mean total sunspots numbers, and year by group by years dot sum, and data head. So and then we want to see my data like this. So let's see, now it is converting into the years. So monthly mean total sponsors has been given, but it has been converted like yearly. So I hope it's clear. Now the plotting the yearly data, so import a matplotlib.pyplot as a plt, and ax will equal to data dot plot. Ax sets x label, so sunspots, and just I am going to plot this. So let's see. Yeah, I think now it's clear. So you could see here your data like this. So first you have plot what type of the variations and we are working with. So whenever just a plot, we could see here like looking at this plot, the pattern is already strikingly clear, and high peak on a regular interval Let's see how to use the ARMA model to capture this pattern and to make predictions for the future. The first step, as always, is to verify whether the data is stationary or not. So remember that stationary means there is no long-term trend in the data. So the average is constant over time. When looking at the data, there is no obvious long-term trend. So you can use the ADF, means just I have discussed in the previous video, augmented Dickey Fuller test. And to perform this, so let's try to the apply here the ADF test. So why do we use the ADF test? So it's clear, I think, because my data, is it stationary and not stationary, we want to get here output. So from the states models dot TSA dot states model import AD Fuller, and the result will equal to AD Fuller data, like a bracket start monthly mean total sunspots numbers, and print results, and p-value results like a 1, and if p is lesser than 0.05, like a 5%, the print is stationary, and if otherwise not stationary. So now I want to going here, work this one, and let's see the what is the output. Yeah, I have gotten these output, like, so just a result I have seen minus 2.65, 0.0864, and these are the 1% as this level, 5% is the minus 2.87, and 10% minus 2.57, and 3658, and it's not stationary. So you could see here the not stationary. So the result we obtain when the applying the test is unexpected. The ADF test tells us that the data is not stationary. In this case, what should we think? So in this case, like a decision would be assumed like a stationary. Decision should be like a stationary. While because ADF tells you not to, a choice has to be made. So we have already one more choice. So let's skip the easier to the possible and say with the original data, like. So now the second things to look at the autocorrelations functions like ACF and the PACF, like a partial autocorrelation functions. So remember that ACF and PCF plots can help you to define whether you are working with AR or MA process. So let's try you. So let's try this one, like from states model dot graphics dot time series analysis plots, import plot ACF and plot PACF, import matplotlib pyplot and plot ACF data I have given, plot PACF and data I have given, and lag I have taken 40. Let's see the plot. So here, so now just I have written, now I'm okay. So I want to see, look here, yeah, let's see, it has been plotted like autocorrelations and correlations, both has been plotted. So autocorrelations, we could see the ACF and PACF plot in this figure. These are the great cases to study the time series pattern. Really very important, and it is rare to observe such a strong pattern in the real life data. Remember from this previous already we have discussed in the previous video. So these are the pattern and we should be looking like AR processes are recognized by exponentially decaying partial autocorrelations, and another is partial autocorrelations decaying towards zero. Look here, towards zero. It's a negative here, autocorrelations, and it's a negative to positives. So swing between the negative and positive partial autocorrelations. AMA process is identified by the sudden spike in the ACF and PACF. So this means that the sunspots cases you have a strong indicator for observing an AR pattern. So this is because you are in the spike. Okay, so this is the strong indicator for observing like a AR pattern, and there is the exponential decay in the PACF together with the switching from a negative to positive. So there is no real evidence for MA process when looking at this plot. So after that ARMA, we will apply ARMA model being a simple and combinations of the ARMA model. And so let's the fitting the ARMA model, and it's clear just means it is important to the realize that there is an optimization going on that finds the coefficients of the model that minimize the mean square error. I have already discussed this MAPI mean square error, and this is the same approach has been already I have discussed, so don't worry. So from the sklearn dot matrices like import R square scores and stats model TSA ARIMA dot model import ARIMA. Now I am using like a forecast the first ARMA 11. So more ARMA data monthly mean total data and monthly and order I have taken 101 because it is using like a ARIMA. So I must be the 0 because I am using ARMA, not a I. I will discuss in the after this. So how do we use the ARIMA? But machine learning it's like a ARMA also used like a ARIMA models, and are residuals like a mode.fit and predictions like a residuals.predict and print R square scores data predictions. And after that I try to the plot like this data and plot the predictions also and legend the actual sunspots and predict sunspots and label like a time steps already given and penalty also. So in this here like the coefficients are estimated by the model, and where the hyperparameter must be the chosen by the modeler in the ARMA PQ model. P and Q are hyperparameter that you must decide on the using of plots like a performance matrices and more. So let's start, and we can see like if I write ARMA 11 model in a like in Python, so we can see here ARMA model with a AR component with the order 1. This one means order 1, and similarly MA components with the order 1. So remember, keep in your mind that the order refers to the number of historical values. I am repeating the number of historical, so it refers, order refers to the number of historical values that are used to explain the current value. So for this first trial with the order 11 to the choice, just start with the simplest ARMA model possible, and throughout the example you will see how to find the tune this decision. So apply ARMA 11 model for the sunspots data means that you will explain like a tomorrow value by looking at today actual value like AR parts and today error MA parts. So after that, just if I am going to run this data, we could see what is the output in this data. So let's see here. So exactly actual sunspots and predicted sunspots both are looking very good, and you can see also like your R square is the 76. It really it's not a very good, but it's good. So in this code, the actual bias, the fitted values, so it will also give and the R square scores of the model fit, and since you have not yet created a train test splits, so this R square is not a prospective of any future performance, yet it can be used to see how wrong the current models is. So this gives an intuitions on how to improve the models, and in this case with the R square is 0.76, so you can conclude that the model is already fitting not too badly. So we could brew here, and after that let's see, we could see, and this is the actual value as the like a fitted value. So I hope you can understand these concepts, and after that let's try here the more model evaluation like the KPIs and is the performance matrices. So I want to take opportunity to inspect a few more model fit a KPI. So you have seen how to use the augmented decay Fuller test to help you decide in differentiations, and you have seen ACF and PACF plots already we have seen here, and help you we decide on the types of model needed like AR, VAS, MA, and to help and we choose the best order. But we have also seen like a train test split combined with a hyperparameter search to identify the order the maximize out of the sample performance. So let's the additional, this is the additional like a KPI. So KPI can help you evaluate a model fit is to look at the residuals of your model. If the model has a good fit, you will generally observe that the residuals follow the normal distributions. If you find the opposite, so your model is generally missing out important informations. So you can make a like a histograms of a residual, and I am going to write here the algorithm, then we will. So here the AX will equal to PD dot series and residuals dot resids dot histograms, and just I have mentioned some Y level and X level like a residuals. So let's see and decide. So it's yeah, look here in this data. So after, so we should obtain from this graph here like a histograms residuals of the ARMA. Okay, so you could see here like this one, it's not a exact bell shapes you can say. So we can observe the visually at the histograms of the residuals is not a following the bell shaped curve, that is a normal distributions. This means that there are probability some lags to be added. There are probability some lags to be added, which is a logical. So you already know that the sunspots data has a 11 years seasonality, and for now there is a only one lag period like a 1 year back. Lag period means 1 year back. So include in the model. So you can take like a 2 year, 3 year, 4 year back and forward it. So don't worry. So there are many different approaches for testing and distributions for the variables, and this includes like a histograms, like you can also QQ plots and numerous hypothesis tests. Okay, so many, don't worry. So although the hypothesis tests for the normally are the useful in the many cases. So the goal of the forecasting is generally to maximize the future performance. So it is not necessary to have residuals that has perfectly normally distributed for this purpose, and a graphical way to of identify the normality of residuals is generally sufficient in a practice. So let's see, just when we have evaluated the normality of the residuals of your model, you can also look like the some, so if you, I want to see here the like the some summary. So let's see here, I am going to write here some algorithms to want to see the some summary. So import numpy as a np, impy as a np. I think just I have, okay, I didn't see here like a residuals, and look here residuals summary. So you could see here like this one, yeah. So I have gotten like a result of this summary. So you could see the dependent variable like a y is a dependent variable. Number of observations I have taken like a 273, and model ARMA, and log likelihood has been described like the -2000, date just today like a 15th Jan, and we could see the AIC and BIC. I will discuss HQIC, these are the very important part, sample 0, and we can also see here, these are the important part here, coefficient, standard error, Z and p value all are the zeros, and here 0.0 lower and higher range, it's a lower like a 2%, and here you can see like a 90%. So what do we see here? We can see whenever I get summary tables of ARIMA 11 model, the important pieces of informations that we can get from this table are the estimated of the coefficient of corresponding p-value. It's clear. So remember that you are working with the ARMA 11 model, and that you therefore will have one coefficient for the AR model for the data point one time step back, and one coefficient of the MA model error in one time step back. So when you fit the model in the data, your model is estimating the best possible value for those coefficients. So you can see the estimates of the coefficients in the table on the line that says AR-L1. Look here, AR-L1 coefficient like a 72, it's good, and standard error is the only 5%. So the AR coefficient for the first lag is the 72. So on the line it say MAL1 like a 52. So you can interpret those by the looking back of the formula. So it basically those estimates state that you can predict the future data point by fitting in ARIMA formula using a constant like a C L1 and coefficient phi and MA L1 sigma and theta. So the filling in those coefficients would allow you to compute the next value. So this is the great information to understanding what information is used by your model to predict the future. So now you know the estimate the value of your coefficient, and you can also look at the hypothesis testing for those coefficient. For each coefficient this the summary table shows a hypothesis test, and that tells you the whether the coefficient is significantly different from a 0. So if the coefficient were to be 0, this would mean that it is not useful to include the parameters. So if the hypothesis test provide that a coefficient is significantly different from 0, and this means that it is useful to add the coefficient in your model, and this help you in deciding which order to use your ARMA forecast. So look here, the p-value of the hypothesis test can be found on the line of the coefficient under the column p is greater than z, and this column gives you the p-value of the hypothesis test, and the p-value must be smaller than 5%, and to prove that the coefficient is significantly different from 0. So in this case, the interpretations like a p-value of ARL1 coefficient 0 so significant, p-value of MAL1 so it's a significant, and both are the smaller than 5%, so therefore we can conclude both coefficients should be retained in the model. So this is a very useful information when creating a model, so you can go back and forward it between the increasing and decreasing the order of AR, like a 2, 3, 4, depend on you, and try to find the which point the coefficient starts to become insignificant, like a p-value higher than 5%. So in which case you take a order of the highest lag, and that was still significant as the best model, and of course keep in mind and significance one indicator between the multiple indicator. After that we can also use like a automated hyperparameter tuning. So this was the code. I think you could see here, this is all this code, and we can use here like this test, and we can plot here. So I hope this video will be helpful for everyone, and I think we will discuss in the next class like a, and we can also like a grid search, like a turning the predictive models like a auto correlations ACF and partial model residuals and summary. So it's the best way to understand this data like ARMA, and thank you very much. Next class I try to discuss like a ARIMA model. Thank you.